Welcome back everyone. In this lecture we will actually prove the Weyl dimension formula. It is a very useful formula to compute the dimension of this irreducible finite dimensional representations of SLN plus 1. So, let us write down the formula. Here is the Weyl dimension formula. So, what this formula says, so given lambda dominant, so we are interested in computing the dimension of V of lambda. So, this is again given by the ratio between the two elements, the product alpha in delta plus lambda plus rho, the inner product with alpha divided by the product rho comma alpha, alpha in delta plus. So, this is very explicit formula. Now, given lambda, it is easy to compute what will be the inner product between lambda plus rho comma alpha. So, then you take the corresponding product and divide by the product rho comma alpha. So, this gives you the formula for this dimension. So, how one can prove this? Again, this can be obtained as application of Weyl character formula. So, what we need to do? We need to actually specialize the coefficients. So, what can think the Weyl character formula happening inside the group ring Z bracket lambda. So, then one can identify that with the Lorentz polynomial ring, and then so it will be polynomial in some xi and xi inverse. So, now you can specialize that xi to some q powers. So, that is what we are indeed doing in order to prove this Weyl dimension formula. So, let us do this very systematically. For that purpose, first we need to define these maps called theta of gamma. The theta of gamma, which is defined from our group ring to the formal power series over reals. So, what is this? So, this is given by theta of gamma e power mu mapped to the exponential of mu comma rho times t. So, mu comma gamma times t. So, this basically you take the exponential power mu comma gamma times t. So, this is usual exponential. Okay. So, now this is map from this group ring to this formal power series. You can extend this linearly to all elements of this Z bracket lambda. Then you can verify that one can comfortably do computation with this map theta gamma. So, this is indeed algebra map. So, now let us actually prove this following identity, which is in some sense elementary. So, if you take theta of rho and apply it on S lambda plus rho, so then you can see that this is exactly same as theta lambda plus rho applied on S rho. So, this is the most important identity that will be used in order to prove the Weyl dimension formula. So, let us verify this and then after that the proof will becomes very clear. So, what is S lambda plus rho? Again let us recall S lambda plus rho given by sine of sigma e power sigma lambda plus rho sigma in W. So, now if you apply theta rho on this, the theta rho of this is going to be theta rho applied on this. So, which is going to be exactly equal to summation sine sigma the exponential of sigma lambda plus rho comma rho times t. So, where sigma runs over W. Now, note that the inner product sigma lambda plus rho comma rho is going to be exactly equal to lambda plus rho times sigma inverse rho, and the sine of sigma is same as sine of sigma inverse. So, using these two observations you can rewrite what is there on the right hand side. So, that is going to be exactly equal to summation W in W sine of sigma the exponential lambda plus rho comma sigma rho times t. So, now the inner product is indeed symmetric. So, this is same as summation sine of sigma exponential sigma rho comma lambda plus rho times t, where sigma in W, and this is exactly equal to theta of lambda plus rho applied on S rho, because S rho is nothing but summation sine sigma exponential sigma rho. So, this proves that theta rho of S lambda plus rho is exactly equal to theta lambda plus rho S rho. So, now we will use this observation to compute what is this theta lambda plus rho of S rho. Note that S rho has this following expression. This is given by this e power rho times product 1 minus e power minus alpha, alpha in delta plus. Now, if we use this expression of rho and then rewrite this, so this can be easily seen that this is exactly equal to e power minus rho times product e power alpha minus 1, where alpha runs over delta plus. So, now if you use this theta lambda plus rho applied on S rho, then because this is algebra map, you can actually take in this theta inside, and then if you carefully do the computation, you can easily see that this is exactly equal to exponential lambda plus rho comma minus rho times t, and then product exponential lambda plus rho comma alpha times t minus 1, where alpha runs over delta plus. So, this is what we get. So, now if we use this expression for the exponential, so e power x is nothing but 1 plus x square by 2 factorial plus etc. So, if we use this, then you can rewrite this as follows: theta lambda plus rho of S rho is given by this exponential lambda plus rho comma minus rho comma t. So, here, so this is going to be e power x minus 1. So, it starts with x, which is lambda plus rho comma alpha times t. So, this is going to be just product lambda plus rho comma alpha t, alpha in delta plus, and then plus some higher terms. So, higher terms means higher terms in t powers. So, this is the term that we are getting on the right side. So, this is exactly equal to, so what we can do, we can just simply, so because this exponential is going to be 1 plus some order of t. So, this is also some order of O of t. So, if you use this, then you can write this theta lambda plus rho S rho to be product lambda plus rho alpha, alpha in delta plus, plus, so t power n you can take it out, where n is the number of positive roots. So, then this is t power n times the product lambda plus rho comma alpha plus this O of t. So, that is what you get. Similarly, if you put lambda equal to 0, you can see that theta rho of S rho is exactly equal to t power n product. So, lambda is 0, rho comma alpha, alpha and delta plus O of t. This is what you get. So, now you can see that S rho chi lambda is nothing but S lambda plus rho. So, now if you apply theta rho on both sides, you can see that theta rho of S rho times chi lambda is equal to theta rho of S lambda plus rho, which is exactly theta lambda plus rho of S rho. So, this tells you that this is exactly equal to theta rho S rho times theta rho S chi lambda, which is exactly theta lambda plus rho S rho. So, now what is theta rho chi lambda? So, that is by definition of chi lambda, you have summation the multiplicity of mu in lambda e power mu. So, this is going to be exactly equal to summation the multiplicity of mu exponential of mu comma rho times t. So, this is what you get where mu runs over all elements of lambda. So, now theta rho S rho, we already have this expression, we can just substitute there. So, you get exactly t power n product rho comma alpha, alpha in delta plus the higher order terms plus summation m lambda mu, mu in lambda plus the higher order terms, which is equal to t power n product lambda plus rho comma alpha, alpha in delta plus the higher order terms. So, now you can cancel this t power n and t power n on both sides and then set t goes to 0. So, then it gives you exactly the product rho alpha, alpha in delta plus times. So, this is going to be the dimension of V lambda. So, times this is equal to the product lambda plus rho comma alpha, alpha in delta plus. So, this proves that the dimension of V lambda is exactly equal to product lambda plus rho alpha, alpha in delta plus divided by product rho comma alpha, alpha in delta plus. In one go, this is product lambda plus rho alpha divided by rho alpha, alpha in delta plus. So, now note that we can also replace alpha by h alpha. So, if you replace alpha by h alpha, the identification is h alpha is just given by twice t alpha divided by alpha alpha. So, if you use that, you can also rewrite this dimension in terms of the pairing, then this is just exactly product lambda plus rho of h alpha divided by rho of h alpha, alpha in delta plus. So, this is just immediate. Okay. So, this tells you that in case if you can compute this lambda plus rho comma alpha, then that immediately gives the dimension of V lambda using this formula. Okay. So, this proves actually the Weyl dimension formula. So, now I will make some remarks about this character formula for type A. So, in type A, because we are involved, we are only getting involved with the Weyl group, which is the symmetric group Sn plus 1. So, one can rewrite everything in terms of determinants. So, we already know that very explicitly the determinant formulas. Okay. So, now if we use those determinant formulas, we can rewrite everything in terms of determinant. So, let us first rewrite what will be this denominator identity. So, if you recall, the denominator identity says, so when G is Sn plus 1, so the Weyl group is nothing but Sn plus 1. So, now you can write rho in terms of the epsilon I basis. Recall that rho is nothing but omega 1 plus etcetera omega n in terms of the fundamental weights. So, this if you rewrite in terms of the epsilon basis, this is exactly n times epsilon 1 plus etcetera n minus 1 times epsilon 2 plus etcetera plus twice epsilon 2 plus 0 times epsilon 1. So, this is going to be your rho. So, rho is identified with the tuple n, n minus 1 and so on 1 comma 0. So, now if you take the sum side of the denominator identity, you can see that summation sigma in W sine of sigma e power W rho can be written as follows. So, now rho is written in terms of this epsilon I basis. So, this is n epsilon 1 plus n minus 1 epsilon 2 plus etcetera plus 0 epsilon 1. So, if you use this basis, okay, so then you can easily see that if you write W rho, so this is going to be n epsilon W of 1 plus etcetera plus 0 times epsilon W of 1, sorry, I am using both notation. This is going to be n times epsilon 1, this is n plus 1 and this is n, and similarly this is n plus 1, this is n plus 1. Okay. So, recall the Cartan algebra. Okay. So, in terms of epsilon i's, we have this n plus 1 epsilon i's. So, that is basis that I am using and rewriting everything. So, now this exponential e power W rho, if you identify with e power epsilon I with xi for I ranging from 1 to n plus 1, then this e power W rho becomes exactly x W of 1 power n etcetera x W of n plus 1 power 0. So, that means this summation can be rewritten as summation sigma in Sn plus 1 sine of sigma x sigma 1 n x sigma 2 n minus 1 etcetera x sigma n plus 1 0. So, this is what you get, but this is, if you think about it, this is the determinant of this xi power n minus j. So, now if you actually use the determinant formula, okay, because everything is given in terms of this alternating sum. So, use directly the determinant formula, you can see that this is exactly equal to the determinant of, so let us write this as xi n minus j, where I and j will run over 1 to n plus 1. Sorry, here because I am running over n plus 1, this should be n plus 1 minus j. Okay, so, this is the determinant, and what will be the product side? The product side is going to be e power rho product 1 minus e power minus alpha, alpha in delta plus. Now, recall that delta plus is nothing but epsilon I minus epsilon j, where 1 less than or equal to I less than j less than or equal to n plus 1. So, if you use this, then you can easily see that this is exactly equal to e power rho. E power rho is given by x power x1 power n, x2 power n minus 1 etcetera xn plus 1 power 0. Then the product 1 minus, so alpha being equal to epsilon I minus epsilon j, minus alpha will be epsilon j minus epsilon I. So, this gives exactly xj divided by xi, where 1 less than or equal to I less than j less than or equal to n plus 1. This is what you get. So, now if you just cancel things out, then this gives you exactly product xi minus xj and then divided by this x1 power n, x2 power n minus 1 etcetera xn plus 1 power 0, which is same as the numerator x1 power etc. xn plus 1 0. So, these two things get cancelled. So, you get this product. So, that means the product side is indeed the product xi minus hj I less than j, and the sum side is nothing but the determinant of xi power n plus 1 minus j, and this is indeed exactly the van der Waals determinant. So, the sum side and the product side of the denominator identity corresponds to van der Waals determinant. So, that is observation we can make for type A. So, now what is about general formula? So, if you go to the general Weyl character formula, so given lambda, so we can actually make it as a theorem. So, given lambda, let us fix to be lambda 1 etc. lambda n plus 1 in terms of the epsilon I basis, summation lambda I epsilon I range from 1 to n plus 1, let us say, which is dominant. So, that translates into all the lambdas are all non-negative integers for I ranging from 1 to n plus 1, and this lambda 1 they are non-increasing, they are actually decreasing, lambda 1 greater than or equal to lambda 2 etc. lambda n plus 1. So, now if you take this chi lambda, you know that this is given by S lambda plus rho divided by S rho. We already seen that S rho is nothing but product xi minus xj I less than j. So, now let us rewrite S lambda plus rho. So, S lambda plus rho, if you think about it, what is lambda plus rho? Lambda plus rho is nothing but lambda 1 plus n, lambda 2 plus n minus 1 and so on, then lambda n plus 1. So, this is the tuple. So, now if you think about it, this is going to be exactly summation sigma in W sine of sigma e power sigma lambda plus rho. So, then if you use this notation, then if you just rewrite this e power lambda plus rho sigma. So, this is going to be exactly, so sigma lambda plus rho is going to be lambda 1 plus n epsilon sigma 1 plus etc. plus lambda sigma n plus 1, that is what you get. Lambda n plus 1 times sigma, some epsilon sigma n plus 1. So, this term, the exponential becomes exactly equal to x sigma 1 power lambda 1 plus n, x sigma 2 power lambda 2 plus n minus 1 and so on, x n plus 1 x sigma n plus 1 power lambda n plus 1. So, that is what you get. So, that means this S lambda plus rho is nothing but summation sigma in Sn plus 1 sine of sigma. So, you get this x sigma 1 power lambda 1 plus n, x sigma 2 power lambda 2 n minus 1 times etc. x sigma n plus 1 power lambda n plus 1. So, which is nothing but the determinant of x I power lambda j plus n plus 1 minus j. So, this is exactly the term that you get on the right side. So, then you can write this chi lambda using this determinant formula. So, this is exactly the determinant of xi power lambda j plus n plus 1 minus j divided by the determinant of xi power n minus j, where this is n plus 1 times n plus 1 time matrix, n plus 1 times n plus 1 matrix. So, this actually writes down very explicitly the character in terms of the determinant. So, this is actually kind of one way to define the Schur polynomial or the Schur function. Okay. So, given this tuple lambda 1 etc. lambda n plus 1. So, this chi lambda which is given by this ratio of this two determinants. So, this is called Schur polynomial. The important thing about this Schur polynomial, it is a symmetric polynomial, and one can prove that this symmetric polynomial, they form a basis for the set of symmetric polynomials in these variables x1 etc. xn plus 1. Okay. So, this n plus 1 is actually confusing a lot. So, one can actually just take SLN and then work with only n variables. So, if you take SLN, then obviously the polynomial algebra is going to be in the variable x1 etc. xn. So, where xi you identify with e power epsilon I. So, now naturally the symmetry group acts on this polynomial algebra C x1 etc. xn. So, what we are interested in? We are interested in this set of symmetric polynomials. So, those polynomials which are invariant under the action of Sn. So, this is called the set of symmetric polynomials. And the set of symmetric polynomials, they have many interesting bases. For example, it is easy exercise to prove that if you take what is called the orbit sum for any given alpha. Okay, so, given any exponents, let us say alpha, which is k1 etc. kn, which lies inside this z plus power n. Okay, basically ki's are all non-negative integers, that is all we want. Then we can talk about the summation x power sigma alpha, where sigma runs over Sn plus 1. So, what is x power alpha? So, that is just a product xi ki, I range from 1 to n. Now, what is x sigma alpha? So, you just define it as before. So, basically the sigma indeed act on the variables. Okay. So, if you want to think about it in terms of the coefficients, so maybe like let us not put it in the top, let us put it here sigma of x alpha. So, one can easily prove that this is indeed symmetric polynomial. So, this is going to lie inside the symmetric polynomials and this will form a basis. So, for all alpha that runs over z plus n. Okay. So, that is something one can easily verify. So, here is another basis. The another basis indeed given by this S lambda plus rho divided by S rho, which is chi lambda, which are the Schur polynomials. So, if you take this chi lambda, where lambda comes from lambda plus, so this also form a basis. So, this also form a basis for the set of symmetric polynomials, the bracket Sc bracket x1 etc. xn power Sn. So, we almost proved this because we already proved that if you take some f being antisymmetric polynomial, so then you can write that as some symmetric polynomial times S rho. So, that actually tells you that so the other way is also true, like so if f is okay some g times s rho and g is going to be the sum of this chi lambda. So, that is what we actually proved. Okay. So, maybe you can directly try to prove. So, if you take some f which is from this symmetric polynomials, so then that implies that f s rho is going to be antisymmetric. So, that is obvious to see. So, f s rho is being antisymmetric. So, that will imply that you can write this f times s rho as summation a mu s mu plus rho. So, this is something we already proved. So, then this implies f can be written as summation a mu s mu plus rho divided by s rho. So, that means f can be written as summation a mu chi mu. So, this proves that any symmetric polynomial can be written as sum of the linear combination of this Schur polynomials, and it is easy exercise to prove that these Schur polynomials will form a linearly independent set. So, that way you can actually prove that the set of Schur polynomials that will form a basis for this set of symmetric polynomials. So, then what one is very much interested in, we want to actually explicitly write down some combinatorial model. So, from that information we will be able to recover this Schur polynomial. Okay. So, that is actually given by this semi standard Young tableaus. So, I will not have time to prove this fact, but I will actually state the result, and then I will give you the correct reference where one can actually see this proof. Okay, I will stop here, and we will continue in the next class. Thank you.